Hello. So today I want to use the online disassembler and object dump to actually solve some real life problems. These are fabricated problems, but these are a really good way to use and learn how to use object dump and the online disassembler. So what we're going to be doing is we are going to be looking at some of the exercises from exploitexercises.com. And this time we're going to do protostar, which is a series of challenges, and we're going to do stack 2. Now, if you haven't checked out exploitexercises.com yet, you really should if you're into reverse engineering or exploit development or CTFs or anything like that. It's a really good series of challenges that hit you on one thing after another or one topic and let you build on that, and then they build off of that. So you deal with one thing at a time, and you can learn in little bite-sized chunks. What we're going to do is we're actually going to solve a problem where they give you the source code, but we're not going to use the source code. I'm using this just because, again, I think this is a perfect example of binary that you can reverse engineer with object dump and the online disassembler. If you haven't been to Exploit Exercises before, what you have to do is go to their website, click on download, click on the protostar download from their Google Drive, save it. It's an ISO, and you're just going to boot that ISO within a VMware player. I'm not going to go into how to start up something in VMware player. You can Google that yourself. But I have to warn you, do not try Nebula. If you go here and you say, oh, this is cool, I'm going to try this. I'll try this Nebula because it's easier. Do not try Nebula. Nebula is not easier. I don't understand why they have Nebula first. In a way, it is easier because there's really no tough. This is Exploit Exercises is really not so much a reverse engineering challenge, but exploit development, vulnerability research type of challenge, or CTF type challenges. And Nebula doesn't have the traditional exploit type stuff. It's supposed to be easier, but I really don't think it is. I think it's a lot harder because rather than any of the concepts that you might have learned and things that you can look up and read and research, Nebula is just a bunch of random knowledge you have to know. And if you happen to know that random knowledge, the solutions are pretty easy. But I really don't think that's great for CTFs or vulnerability, learning about vulnerability and exploit development, or learning about reverse engineering. I don't really think. I think their first one, the Nebula, is actually really off-putting to people who might be new to it because it's just random stuff you might have to memorize, and it's not organized in a very good way where it leads you from one to another. Whereas the protostar is great. So I recommend you jump into protostar if you want to try it. But we're going to go ahead and do one of the exercises. Again, we've downloaded the protostar ISO. We started up in a VM. And I'm just going to go to the exercises. I'm going to click on the protostar. I'm going to click on stack 2. And they give you the source code, but don't look at the source code. Actually, we don't even want to go to that page. We just want to look at how to get into it. Getting started. Once a virtual machine is booted, you are able to log in as a user account with a user password. So that's what we're going to do. So I've started this VM. And logged in with user and user. One of the things I'm going to do real quick is I'm just going to get the IP address. Type sbin ifconfig, hit return, and I'm going to get the IP address of this machine because I'm going to SSH into it from another machine. So it's 192 in my case, 168.79.140. So I'm going to go ahead to my other VM. Open my terminal, and I'm just going to SSH. Actually, let's make a directory. Let's do make dir exploit exercises. CD into there, and now I'm gonna make a directory for stack 2 and CD into there. And now I'm just going to SSH into that machine. Okay. And the binary was an opt protostar bin, and that's all in the informational page for exploit exercises protostar. And we want stack 2. So I'm going to go ahead and download this to my desktop. So in another window, I'm going to cd and exploit exercises, stack 2. Then I'm going to just SCP it. SCP 192.168.79.40. Actually, I have to SCP user at, that's the username at that machine. I want to grab the file opt protostar bin stack 2, and I'm just going to copy it here, which is the dot. Give it the username, and it's there. So now I have stack 2. And I can type file stack 2 just to make sure it's the right file. And yes, it's a ELF32-bit executable. So this is what I want. You can go ahead and close. We'll leave that window open. We'll just minimize it. Now, so I have the stack 2 here. I'm going to clear the screen. And there's a couple things I want to do. I want to load this into the online disassembler. And what I want to do is use the online disassembler to help me reverse engineer the problem. Unfortunately, one of the things that the online disassembler doesn't have is a feature that Object Dump has, which labels known functions for you. And I'm hoping they'll add that. I actually talked to the owner, or the gentleman who is part of the team that maintains that disassembler. And so I sent him an email and mentioned that. So hopefully maybe they will add that as a feature in the future. So let's go ahead and let's just obj dump this. So obj dump, we've used it before, minus j.text, minus d for disassemble, minus capital M intel, and stack 2. And we want to see the main binary, or the main code. Here we go. Here it is. Now, the reason I'm doing this and not just using the online disassembler is because when I do it on the online disassembler, all my calls are just going to be call at function at this address, whereas obj dump actually gives me the names of what I'm calling. For example, this get an env gets an environmental variable and gets you a pointer to it. String copy. Hopefully you know what string copy is. It copies a string from one place to another. Puts, which prints out information. Printf, which prints out information. And that's going to help me just because when I go in the online disassembler, I'm going to go immediately label the functions that I know what they are based on this. Okay? So let's go ahead and get the online disassembler out. So I have my terminal window. I'm just going to start up Chrome. Hopefully you're using Chrome. Chrome is an excellent browser. And let's go to www.onlinedisassembler. If I can learn to spell. That's the problem with spell check, is it really crushes your ability to spell for yourself after using spell check for so long. So let's start disassembling. Right? I'm going to click on Start Disassembling. Excuse me. Let's go ahead and File, Upload File. We will do Choose File, and we are going to go into, this time we're going to go into Desktop Exploit Exercises, Stack 2, and the binary is Stack 2. Project name, Stack 2 is fine. Let's click OK. Now, let's make sure to set our disassembly options to Intel, unless you specifically prefer AT&T format. Okay. And click OK. It will do its thing. And you see here, let's click on main. Here we have the main function. And if I'm going to go ahead and minimize this a little bit, just try to bring it side by side with the code that obj dump gave us. So if you watched my other video called Using obj dump to Augment the Online Disassembler, you know that the Online Disassembler by default doesn't show the function names from imported functions, where obj dump does. For example, string copy, put s, whatever. So I'm going to go ahead and quickly use obj dump to populate the function names here in the online disassembler. And again, if you aren't familiar how to do that, either watch with me real quick here. I'm just going to go real quick through it, or go back and watch the video where I explain it. Again, that was using objdump to augment the online disassembler was the name of the video. So get env over here. We're going to name that get env. The next function was error x. Oops. Where'd that go? The next function was string copy. And then we have puts. And finally printf. So great. Now we shouldn't need this anymore. I believe we have everything labeled. All the calls are labeled. So we can go ahead and close down. Yep, we can go ahead and close down that objdump window. Go ahead and maximize that. So now we can get to the task at hand, which is to reverse engineer this binary and try to figure out how to capture the flag. That is, we want to figure out the input that is going to get it to print out the thing that says basically we won. So one other thing I want to do real quick is I want to go ahead and label in main anywhere where there's a print puts or a printf. I want to go ahead and label that with the string that it's going to print, because we want to see what code flow where we want to get to. So let's, and again, remember in the stack 2 exercise, exploit exercises, you get the C code. So you can actually kind of see what's going on. But we want to do it without that, although we do need to know that what's the purpose of what we're trying to do, right? So I'm going to just tell you the purpose is to capture the flag, to get it to print a certain, to get it to flow down a certain code path and print the certain, hey, we won, basically. So let's figure out where that is by figuring out, you know, what is being printed. So anywhere we see a put s or a printf, let's go ahead and label that with the thing that it's going to print. So where is our first puts? So our first puts is here. And puts, if you know anything about puts, puts will print a string. The string is the first argument to, and the only argument to puts. Let's just do a man on puts real quick. You can see puts is int, it returns an int, puts constant char pointer s. So it takes one argument, one parameter, which is a pointer to a string, and it's going to return an int. Let's actually go ahead and label that. Let's click on puts, and actually let's go ahead and fill that in. Create edit function. Function returns an integer, and the function arguments is const car pointer. Great, so we have that labeled. Now let's go ahead and figure out what actually puts is actually printing for us. When puts runs, it's going to look at the stack for its argument. So we have to look to see what was pushed to the stack. Now in this case, the way the compiler did it, rather than using push, it actually directly accessed the stack and directly wrote to the value, to the address of ESP where it currently is pointed to. So in this case, it's not going to actually be a push. Here is the line that actually is writing the parameter to the, or I call them arguments. Some people call them parameters, some people call them arguments. The argument to the function putS. It's pushing this memory location, or writing this memory location. It's not pushing, technically, to the stack. So let's figure out what that memory location is. We know that's going to be a string, so let's go to strings. It's 804.8618. So 804.8618. Okay, you have correctly modified the variable, and we can see that here. So, and I think I actually missed a put s. Let's go back and start from the beginning. So on this line here, let's just type comment and type you have correctly modified the variable. Great. And let's go to the other ones. In this case, we have printf, so let's click on printf. Let's go ahead and label printf. Do we know what printf takes and returns? Printf is a little more difficult. Printf returns an integer and takes a constant char format and then variable arguments. So let's go ahead and just update the function signature with that information. It's going to return an int, and it's going to take a const char pointer and variable. I don't know if actually how the online disassembler is going to handle that. Okay, it looks like it did. Great. So now let's go ahead and back to where puts is called. Let's get back to our symbols, go back to main, and let's see where printf is called here. Okay. And what is it printing? Well, it's moving to ESP, to the stack, whatever is in EAX. And we can see back here, if we go a couple steps back, EAX is set to this memory location, 804.8641. Let's see what's there. 804.8641. Try again. So we're going to go ahead and label this. Try again. Okay. And then finally, let's see if there was any other puts that we missed. I thought we missed a puts here. I guess maybe not. I could have swore we missed a puts. Call get NV, call error X. Okay, so error X actually is the one that's printing the other error. Let's look at the format of error X. And error X is integer eval, constant char format, and then variable arguments. So we're going to look for the second argument. Let's go ahead and again label though error X with the function signature. It's going to return an int, and it's going to take int const char pointer and then variable arguments. Okay, so let's go back to main. Look at error X, and we know the first argument is that eval, and we're not concerned with what that is. We want to see the string, and the string that it pushes, it's not pushing again, it's writing directly to the stack. The stack plus 4, which would be the second argument. Okay, if you're thinking about how the stack is laid up, the second argument, because you push the right arguments first. So the higher address, if you're pushing them, here we're not pushing, we're writing directly to the stack, but that's going to be 1 4 bytes higher than ESP, so ESP plus 4. So let's see what that string says. That's 804.85E8. There we go. Please set the greenie environmental variable. So let's go ahead and set that here. Please set the greenie environmental variable. Great. So let's go back to our assembly. We now have anywhere that an error message is printed or anything is printed to the screen, we have them all labeled. Let's look at the graph. This is the graph of our program. It starts out over here, makes a decision, does one of these 2 basic blocks, makes another decision, does one of these, and then does one of these 2 basic blocks. And I mentioned we want to get here. We want to get into this basic block. So let's go ahead and, I guess I can't edit that. This is where we want to get, to this area. You have correctly modified the variable. So we are going to have to get in our code. We're going to have to follow from the beginning to the end, either going here to here and then to here. Okay? If we get to this block, try again, we lose. So our point is to get here in the code. How do we do that? Well, let's read the code. So we push EBP, and that's part of the prologue. Then we move EBP to ESP. That's part of the prologue, so that's not real code that the programmer wrote. We're ANDing ESP, which this serves to just do something called aligning the stack. And again, this isn't something, this is basically part of the prologue. When I talked about the prologue, we didn't see this in the video that I talked about the prologue, but this is often, you've seen this, you will see this. And then we're subtracting ESP 60 hex, so it has some local variables there. And again, that's part of the prologue. And that is where the prologue ends. Now, what do we know about this, though? We know that based on this, there are 60 hex, which is what? It's 96 bytes of local variables. So I'm going to go ahead and actually switch back to main here, if I can. And when we do the sub, let's go ahead and label that. Let's just say 96 bytes of local variable space. We might not actually be using 96 actual bytes of local variables, but we're allocating that much space. Okay. And I'm going to go ahead and just edit all. I'm going to put prologue here, prologue stack align, and then we're going to run. And I'm going to, rather than go through the graph view, I'm going to just do it in this assembly view until we get to the end of that basic block. We're going to call getEnv. Well, what does getEnv do? GetEnv gets an environmental variable. It takes a constant car pointer and returns a car pointer. So let's go ahead and edit that in there. GetEnv, we know it's going to return a car pointer, and it's going to take a constant car pointer. Means constant car pointer means that the value that the pointer points to will not change. We know that it takes basically a string, a constant car pointer, and here we go. This is the argument to getEnv, and that's a string. And let's look up what that string says. 5EO. So 5EO, greenie. This is the environmental variable. So it's going to take this look up the value of greenie in the environmental variables. When it returns, the value will be returned in EAX, because when you call a function in this calling convention, the return value is in EAX. So then it immediately moves EAX to ESP5X. So we know that ESP5X is actually, I'm going to write ESP plus 0x5 5x equals value of greenie. All right, and then it's going to compare d-word pointer ESP plus 5x. So it's going to compare whatever the value of greenie is to the null string and jump not equal. So if they're not the same, it's going to jump to this location here. Okay. If it is the same, it's not going to jump. So if it's the same, that means that our value of greenie was not set to anything because the null string is null. So if we didn't set an environmental variable, it's going to print out this message. Please set the greenie environmental variable. It's going to load that onto the stack and call error x. So if we get here, this is bad, right? And the program will we will never be able to modify our variable because we'd never set the variable. So here, if we have set the environmental variable, it's going to jump to this location. I'm going to go ahead and see if I can change the name of that to environmental variable set. So I'm going to click on it. Let's see if I can create edit function. It's not really a function, but I'm going to go ahead and try to just see if I can change this to environmental variable set. I don't know if that's going to work or not. I never actually tried that. And it does. It labels it as a function. It's not really a function, but you know what? That's fine. We'll deal with that. We'll accept that. Okay. Okay. So we'll leave the name in there. It's not really a function, but that's okay. It just says it's a function, but it's not. It's a basic block. But hopefully this won't mess up our graph view. Okay. So let's go back to the graph view and look. If we had set the environmental variable, then the jump not equal is going to be true, and it's going to go down to this path. It's going to move 0 into d-word pointer ESP plus 50x. And let's go ahead and let's go back to disassembly so I can comment it. So it's going to move that to ESP plus 58x, which is what? What is ESP plus 50x? In this case, that is a local variable because we subtracted 60x from ESP. And you can see already, if you watched some of my other videos where they were using EBP as the frame pointer. In this case, they're not using EBP as a frame pointer. They're using ESP directly and offsets from ESP, which is, you'll see sometimes. So this local variable is set to 0. Then we move, we know what this is. This is the value of greenie. We move that into EAX. Then we move that into ESP plus 4x. So let's write that in here. So we know that is also the value of greenie. Then we load EAX with the address of ESP plus 18. Then we move EAX into ESP and call string copy. So what are we doing here? Well, we know a string copy. What does string copy do? It takes two strings and copies one to the other. So destination is the first argument and the source is the second argument. So the first argument is EAX, and EAX is the address of ESP plus 18. That will be the destination for the string copy. Now the second parameter is located ESP plus 4, which is whatever EAX is or was at the time this was executed. EAX at that time was the value of ESP plus 5C, which was the destination of the value of greenie. So then we are going to call string copy. So we're going to copy whatever the value of greenie was into the memory address ESP plus 18. Okay. We'll call string copy, which will do the actual copying, and then we're going to move ESP plus 58 into EAX, and then we're going to check EAX with this integer, DOAODOA. So, and then we're going to check to see if they're equal. If they're equal, jump not equal to location here, where we print the pry again. So let's look at the graph. In here, we call string copy, and then after we call string copy, we immediately check to see if the value, whatever is stored at ESP plus 58, and that's a D word pointer, so it's going to take an integer, it's going to take 4 bytes from this location, ESP plus 58, and compare them to see if it's this, DOAODOA. If it is the same, I'm sorry, if it's not the same, jump not equal, then it's going to go down here, which is try again. Well, we want it to go to here. You have correctly modified the variable. So what we want it to do, whatever is stored at this location, we want to be able to we want to equal DAAODOA. So we have to figure out a way, it looks like, since there's nothing else in the code that we interact with, we only interact with this greenie environmental variable, which gets called a string, which gets copied to ESP plus 18. We need to figure out how to get that greenie environmental variable data, how to insert enough data into that such that it overwrites the data at ESP plus 58. Well, string copy, how does that work? Well, string copy it keeps copying until it hits a null byte. So if we put enough data in there, we will be able to go and basically overwrite this value, ESP plus 58, right? So we need to figure out how much data that needs to be present in the greenie environmental variable to go from ESP18 to ESP58. Well, that's easy. You just subtract 58 because it's both ESP. 58 minus 18 is hex 40, which is 64 bytes. So 64 bytes will get us to this address, ESP plus 58, and then we just need to write in this data here, this value, DOAODOA. Okay? Now, because we're little endian, we have to be careful. We're not going to write DOAODOA. We're going to write it backwards, OAODOA. Okay? So let's see if that works. So let's SSH into our remote exploit exercises virtual machine. And let's just start a bash and cd do opt protostar bin. And it was stack 2 we wanted to do. So let's just run stack 2 without doing anything, giving anything. And it says, stack 2, please set the greenie environmental variable. So we expected that because we didn't actually set the greenie environmental variable. So we are taking this path where there is no environmental variable set. So the check to see if the greenie environmental variable's value is nothing is true. So jump not equal, that would be if it's set. Since it is not set, since it is equal, it jumps to here because a null string is 0. So it then says, please set the greenie environmental variable. Okay, great. So let's set the greenie environmental variable to just anything. And the way you set an environmental variable, if you're not sure how to do that, is export the variable equals whatever you want it to be. Okay, and let's try running it with that. And it says try again, you got 0. So that did not work for us. And certainly it did not work because we mentioned that we're gonna need 64 bytes of data, plus we're gonna have to then put this value in, OA, OD, OA, OD. So there's an easy way I could just do export greeny equals and then just type 64 characters. But there's an easier way. So the way we can do this is we can write a Python expression that prints a string and then assign that to the greeny variable. The way we do that is export greeny equals and then put the command you want to run in a $sign and then parentheses, and that will actually run the command inside, and the results of that command will be set to that environmental variable. So let's do that, and then type stack2, and there you go. We have correctly modified the variable. So you can see how just from using the online disassembler to analyze the binary, we could actually compute the exact amount of data. Well, we could actually analyze the flow of the program and then compute the exact amount of bytes that we needed to write to overwrite the value that was required to win the challenge. So hopefully you learned a little bit today about using the online disassembler to reverse engineer problems that you don't have the source to. If your organization requires serious security training, we provide in-house and off-site classes. Check out our website, www.paladingrp.com.